Our goal is to understand how we determine the derivatives of inverse trig functions, inverse sine, cos and tan, and we're essentially deriving expressions for the derivatives. So by now you should be familiar with this result. dy dx is 1 over dx dy, and that result facilitates the derivatives of the inverse trig functions. So if we start with y equals inverse sine x, we know the domain and range are restricted thus, and we get that from the previous work we've done recently. Having recalled the above, then we look at rearranging y equals inverse sine x to x equals sine y. And then we take the derivative. This is where we use our result from the top of our page. And dx dy, using our definition above, would be cos of y. And dy dx would be the reciprocal. One on cos y. Where y cannot equal 0, cos y cannot equal 0, I should say. So cosine y cannot equal 0. Now we use Pythagorean trigonometric identity. Cos squared y plus sine squared y equals 1. At this stage I'm going to, so I can make references to these soon, just call that result 1, call that result 2, and as we know, y is an element of the set negative pi on 2 to pi on 2, based on our previous work. This would mean that cos y would operate over this interval from 0 to 1. You might have to pause and think about that a bit. Call that statement 3. And also, since x equals sine y, we can say from statement 2 statement 2 is the Pythagorean trig identity. So cos squared y, and we're rearranging that, 1 minus sine squared y, where x equals sine y, or sine y equals x, so that would be cos squared of y equals 1 minus x squared. And cos of y, the square root, is plus or minus the square root of 1 minus x squared. But cos of y must be at least 0, so it's generally positive. Thus we take only the positive result. Okay, so cos y is square root of 1 minus x squared. Now we allude back to statement 1, which is up here, and statement 1 was dy dx is 1 over cos y. So applying that down here, dy dx is 1 over cos y, which is 1 over the square root of 1 minus x squared. So therefore, if we have y equals inverse sine of x, dy dx is 1 over the square root of 1 minus x squared. Now, the stipulation is that x has to be between -1 and 1. Okay, so if it equals 1, we can take the square root of 0, but then you have a dividing by 0 scenario. Okay, so there is a restriction on x. Similarly, we can show a result for this scenario here. So the derivative of inverse sine x on a, where a is an element of positive real numbers. So using chain rule, I'm not going to do the entire derivation, but I'll just to show you what substitutions we'd use. So for using chain rule for u, where we've got the familiar chain rule, dy dx is dy du dx. Okay, u would equal x over a, and we'd have a scenario of y equals inverse sine of u, and we'd have du dx would just be 1 on a, and then we'd multiply that together and simplify it. Okay, you could try that yourself if you like. So very similar processes there for inverse cos of x. And inverse cos of x over a. I'll have all of these in one place at the end of the video, so you can copy them down then if you wish, or you can copy them down now carefully. Lastly, tan uses a slightly different approach. So with inverse tan x, we know that x is unrestricted and y is between -pi on 2 and pi on 2 exclusive. Remember all that previous stuff we did. So now what we need to do is rewrite this as x equals tan y, and whether it's from your formula sheet or from using the quotient rule, you know that the derivative is sec squared essentially. So basically dx dy is sec squared y. Okay, so that could be from the formula sheet or just quotient rule. So dy dx is 1 over sec squared y. Using a version of the Pythagorean identity there, and it's generally on formula sheets. Okay, so sec squared y is tan squared y plus 1, but in this case x equals tan y from that result there, and therefore we can sub in, instead of tan squared y, we can put in x squared, and so that would mean that dy dx is 1 over 1 plus x squared. we can use the chain rule. I won't show it here, but you can use the chain rule to show that for the derivative of inverse tan x over a, we can show that that equals a over a squared plus x squared. Now the full results here, so ensure that your notes have these entire results, including the allowable values for x. Okay, so we have, if you know, basically if you're familiar and fluent with the version of x over a, the x bit is just like when a equals 1. So essentially that's what you need to be able to recognize and apply, and it's generally on formula sheets.